Good morning, everyone. Today we're going to be doing significance testing for difference of means. Very excited. Thanks for joining me. And yeah, let's go ahead and get started. All right, that's enough of that. Let's do this thing for real. Okay. All right, grab your weapon. Got mine. All right, significance testing for difference of means. We're doing this right now. This is how it goes. Try watching this in 2 times speed, Alex Hedge. Not going to happen, okay? I'm going too fast. All right, so this lesson is like a combination of when we took a difference of 2 proportions. So it's kind of the same process, except the conditions that we check are the conditions for the difference in means from the confidence interval in 10-4. So same conditions from 10-4 for the 2 populations that we have to check. Same kind of process as the difference that we did before. So for the most part, let's go over the quick changes from this test, between this test and what we've done before. We have a difference of means as our null hypothesis. We usually set them equal to 0. We don't always have to. It can be some value a or something, but it's usually 0. And so the null hypothesis is usually like, hey, these 2 populations are the same. By the way, we can get there by adding mu2 to both sides of this equation, right? That's usually the null hypothesis. And the alternative hypothesis is, well, they're actually different. Or, well, they're actually greater. Mu1 is actually greater than mu2. Or, well, mu1 is actually less than mu2. So these are kind of how we think about them in our head. This is how we state them as hypotheses. So if the difference is 0, they are the same. Okay, let's go ahead and cruise on. So what about our standardized test statistic? Remember, it's always, doesn't matter which significance test we are doing, statistic minus parameter divided by the standard deviation of the statistic. In the last video, we showed the kind of the proof of how you get the standard deviation of a difference of 2 means. So if you want to try and understand that in a deeper manner, please watch that video. The statistic we are using to estimate the difference in 2 population means is the difference in 2 sample means. That looks like this. The problem is we don't know what this here is. The standard deviation of population 2. This is the standard deviation of population 1. We do not know what those are 99.99999% of the time because we're trying to talk about the difference in means, right? There's no way we would really know that. So we don't use a z most of the time. We substitute in here for sigma. For the population, we substitute for what we pulled from the sample. So S1 and S2 are the standard deviation of the samples that we pulled. This is the difference. This is our statistic, what we're using to talk about the difference in population means. And for our test, we're going to use 0 or whatever value is right here for our test. Usually it's going to be 0 for you guys. I think it's always going to be 0 for you guys for the most part. That gets substituted in for mu1 minus mu2 because that's our hypothesized value. Remember, the significance test is always like, hey, assuming that this claim is true. Go back to Dylan. Dylan walked in and he was like, hey, I'm an 80% shooter, y'all. And then Dylan went to the gym and shot 16 shots out of 50, made 16 out of 50. And then we said, Dylan, okay. Look, we're not saying you're a liar, but if you really are an 80% shooter, then this is how rare it is that you would actually get 16 out of 50 shots correct. So that's kind of like, that's how we argue this. We're so, compassionate and considerate of Dylan. And I gotta say, Dylan's one heck of a guy. You can share this with him. I'm being sincere here. He's a stand-up gentleman. Next we go. We are going to forge ahead here. Conditions for the difference of 2 means are the same conditions we check with the confidence interval for a difference of 2 means. Exact same. There's one thing you gotta remember here is this one. We kind of talked about it in our live session, but I did not mention it in the last video. When you're checking randomness, you have kind of 2 different scenarios. There's a scenario when you have to check to make sure that the samples came from 2 independent random samples, meaning independent meaning you sampled from population 1 and that sampling did not affect your sampling from population 2, or 2 groups in a randomized experiment, and those the first ones need to be random as well. 2 groups in a randomized experiment. So you could have volunteers for this and it would be satisfied. You actually don't need to randomly select from a population because you're trying, most of the time in those significance tests, you're randomizing the treatment and you're trying to say something about the efficacy of a treatment. You're trying to say, hey, this treatment has an effect on people like these in the study. Okay, so if that's the case, if you have like volunteers or you didn't randomly select from the population, but the random condition is still satisfied, then you don't have to check the 10% condition because that's only when you sample without replacement from the population. Well, we didn't worry about that, so we're fine, okay? And then down here, normality, remember if both populations are normal or good, any combination of the following for each population. So if one of them is normal and the other one we sampled greater than 30, you're good. But if neither of these two, these are the easy ones to satisfy, then you just check and make sure. If you know that our sample size is less than 30 and we don't know the shape of the population, then just look for skewness and outliers. If you don't have either of those, you can kind of, or strong skewness or outliers, then you can kind of move on most of the time. All right, let's take a look at our problem here. That is the bathtub draining. Apologies. This is Alex Trebek from this amazing 90s ad here. Does the amount of calcium in our diet affect our blood pressure? That's the question. Does the amount of calcium in our diet affect our blood pressure? 21 healthy men who volunteered to take part in an experiment were randomly assigned to 2 groups. 10 of the men received calcium supplement for 12 weeks, while the control group, so 10 guys got calcium, control group of 11 men received a placebo pill that looked identical to the calcium pill. The experiment was double-blinded, meaning the people didn't know what they were receiving, and the people administering the treatments didn't know what they were giving. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative number. So here's what we're doing. Here's the study. We got 21 volunteers, all right? 10 men randomly were put into the calcium group, okay? And 11 men were randomly put into the placebo group. So in each group, what they did, each guy is going to take their blood pressure at the beginning of the study. They're going to take the pill for 12 weeks, and at the end of the study, they're going to take their blood pressure again. And what they're going to do is, since a decrease is noted as a positive change, a decrease is noticed at a positive change. What that means is we're going to do the blood pressure before minus the blood pressure after 12 weeks for each of the guys. Okay? And we're wondering, does it have a change in the blood pressure? Okay? That's the question. Does taking calcium have a change in the blood pressure? Okay, super. Let's go ahead and move forward. Do the data provide convincing evidence that a calcium supplement reduces blood pressure in a different manner than the placebo, on average for subjects like the ones in this study? So, what is it asking us to do? Okay, the keyword for significance test, right here. Provide convincing evidence. Okay, now actually, if you're on the AP exam and they say this to you, you do not have to do a significance test. You can do a confidence interval and say, here's my method of inference. I'm not choosing to do a t-test. I'm going to choose to do a t-interval here. Okay, so you can do that perfectly fine. And you can look and see if the confidence interval contains 0, and then make your decision on convincing evidence and whether or not we have it. All right, so let's go ahead and state, what are we trying to do here? All right, we're going to say, oh baby, we're moving on. We're finally doing something. Okay, H0 is equal to mu calcium minus mu placebo equals 0. We're saying the mean in reduction from the calcium group and the mean in reduction, or rather, basically the mean in reduction for people that like these that are going to take calcium and the mean in reduction for people like these that take placebo, it's going to be the same. Like calcium doesn't have an effect is essentially what the Null Hypothesis is stating here. The alternative hypothesis is that for all people like these that are going to take calcium minus all the people like these that take placebo. So what do we do here? Is it going to be, I think it's not equal because of the phrasing in a different manner. Okay, so calcium could decrease it or it could increase it. And there's nothing in the question that would lead us to believe otherwise. It turns out I've changed the question slightly to make this a two-sided test, but that's okay. We're going to move on. All right, so we have to say, okay, where mu sub c is equal to the true mean decrease in systolic blood pressure. Okay, now this is not for people in our study. This is for all the people like the ones in our study that we could potentially be talking about. For men like these in this study, so the true mean decrease in systolic blood pressure for men like these in this study after, or rather who, took a calcium supplement for 12 weeks. So in order for men like these in the study, okay. Yeah, let's go ahead and move on. I think I could have phrased that a little bit better. For men like these, yeah, that's fine. Okay. And then mu sub p is the true mean decrease in systolic blood pressure for men like these who take, I think it should probably say take a placebo for 12 weeks. Okay, so you on the AP exam would write all of that out. I'm going to change that took to take. I think that makes more sense. Who might take or who would take. Took means it already happened. Makes it sound like it come from the sample. I don't really like that. So I'm going to change that to take. Okay, great. So those are our two means. There's something else we still have to state in the beginning of our test. Before we collect data, we have to state the significance level. So we plan to test at a, what do we want to do here? What do we want to do here? What did I choose before? Alpha, yeah. Plan to test at a significance level of alpha equals 0.05. Nothing was mentioned so if nothing is mentioned in the problem on the AP exam, you can just use alpha equals 0.05, or if you're doing a confidence interval, use a 95% confidence interval. All right, plan. Yeah, let's go ahead and do this thing. We got this. Plan. Let's make a plan. We want to use a 2-sample, this is what we'll use for these, a 2-sample t-test for mu c minus mu p. Okay, we want to use a 2-sample t-test for mu c minus mu p. We have to check our conditions. Random condition. these came from a randomized experiment. So even though they were volunteers in the study, we're still good because we're trying to talk about the treatment, and they came from a randomized experiment. Since they came from a randomized experiment and they were volunteers and we did not sample without replacement from a larger population, we do not have to check the 10% condition. We do have to check the normal/large counts condition. And our samples are right here. This has 2, 4, 6, 8, 10. This has 10 people in it. And this one has 2, 4, 6, 11. That's right, I remember. Whoops. Okay, let's go back. So 10 and 11. So neither of them are the appropriate size. So what we're going to do is we're going to take a look at their dot plots. So I'm trying to think, like, how are you going to do this realistically? I don't think our calculators can do dot plots, or at least maybe you can figure out a way. I did not find a way to do it on your calculators. So I'm just going to plot them really fast. All right, so for the calcium, I'm going to go ahead and graph a line here. Whoa, I guess I had a book in my way. Let's try that again. Much better. Okay, and we're going to center it on 0, 5, 10, 15. So this is what you would probably have to do on the AP exam. -5, -10, -15, and -20. And I'm basing that off my data. It doesn't look we go higher than -20. And I'm just going to go in steps and 5s to save some time. All right, I'm also going to cheat a little bit right now. And I'm going to copy this and drag that down for the next set of data as well for the placebo. So I've got it pulled up on another screen here, so I'm going to be looking at that other screen, but we'll be talking about this data for the calcium group. Okay, so I'll do the calcium group is in black, so I'll do that in black, and then placebo is down here. So here's my placebo, there's the calcium group. All right, perfect. All right, let's go, in black. Pull up the data. Okay, 7. So just go ahead and plot this really fast. Feel free to fast forward at this point if you're feeling comfortable plotting data. Let's go ahead and make it largo. 7, -4, 18, 17, -3. Now it does not have to be perfect necessarily. -5, 1, whoops. -5 and 1, and 10, and 11, and -2. Okay, so there's our data for the calcium group. I think it's perfectly reasonable for us to conclude that these came from a normal population. There's no horribly strong skewness. We could have grabbed a bunch of stuff from just kind of like the middle of the curve here. Perfectly reasonable. So no strong skewness and no apparent outliers either. Okay, and in the placebo group, there was one at -1. There was one at 12. Another one at -1. One at -3. One at 3, one at -5, one at 5, one at 2, one at -11, one at -1, another one at -1, one at -3. Again. And I think that's it. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. Got our 11 data points. So the question is, are these two dot plots different enough for us to be able to say that these data came from two different populations based on our sample? And that's what so we can look and we can speculate, but we need to be able to show it mathematically. And that's what we're doing. That's why this is a math class, ladies and gentlemen. Well, first we have to argue that it's safe to proceed with the test. So what do you guys think here? What's your gut tell you? Is it plausible for these two to have come from normal populations? Okay. I think it is. So the dot plots show no strong skewness or outliers. So it is plausible the data come from normal populations. Remember, we're checking two populations here. So that means we can proceed with our test in all its glory. Let's go ahead and do that. Let's proceed. Yeah, this will be fun. Okay, there's our data. So take a second to plug that into your graphing calculator so you can get your summary statistics. I think you can just run two var stats on these two as well. It should summarize both of them for you, maybe. Okay. All right, let's go ahead and get started. All right, so one thing that you're going to notice once you run the two variable statistics, you'll find X bar for population 1, so X bar C, the mean reduction in blood pressure from the calcium group is 5, and the standard deviation of the reduction in blood pressure from the calcium group is 8.743, and that is the sample size from the calcium group is 10. Let's go on to the next group. So the mean in blood pressure reduction from the placebo group is negative 0.273. So people actually kind of increased from the placebo group. The standard deviation of the placebo group is equal to 5.901, and the sample size from the placebo group is 11. Fantastico. So we've got our summary statistics. We can go ahead and kind of proceed with the test now with our test statistic. Remember, that is equal to X bar C minus X bar P, our statistic minus our parameter, mu sub, whoops. Whoa, not cool, smart notebook. Not cool. I'm writing too fast. Mu sub C minus mu sub P. So we're using this to estimate that, and the standard deviation of our statistic, X bar C minus X bar P, is the standard deviation of C squared divided by the sample size from C plus the standard deviation, so the square root of, I should say, P squared, SP squared, and the sample size from the placebo group. All right, let's plug her in. I wonder if I can fit it right here. Yeah, we're going to do it. We're going for it. For here, that's going to be, the difference is 5, be careful, minus negative 0.273, double negative there, minus, we are assuming for our test that these two are the same, just like we assumed Dylan was an 80% shooter when we did our simulation. So we're assuming they're equal, which means the difference should be 0, and the standard deviation of our statistic down here is going to be 8.743 squared divided by 10 plus 5.901 squared divided by 11. And we get some numbers. Our t-test statistic is going to end up being 5.273, negative and a negative, careful, divided by the square root of, and I'll let you guys do the math, it's the square root of something. Actually, I didn't get the square root of that thing. Let me just do it really fast. Interlude music. Insert. We'll do it in post. We're going to put that in post-production. It's like 2 to the square root of 2.5728-ish or something like that, which is 5.273 divided by 1. Oh, that is not correct. Pardon me. I used the wrong number there. Erase that. Scratch that. Should be the square root of 10.8096. And then that is, looking at the wrong thing, that is 3.2878. All right, so when we do this divided by that, we get a t-test statistic of 1.604. Now that we have calculated the t-test statistic, we can go ahead and use our t-tables to calculate the area for that. We are doing a two-sided test, remember? Since we're doing a two-sided test and we have an alpha value of 0.05, that means we are going to be using 0.025 for the tail here. So really what we're trying to do though is we are trying to, before we get to that, we're trying to see, since we're doing a two-tailed test, we know we have 1.604 here and we have negative 1.604 there. So we are looking to the right and to the left to get our p-value. What are we going to use for degrees of freedom? Well, we can use that horrible degrees of freedom formula, or we'll use the smaller of these two, so and then subtract 1. The smaller is 10, minus 1 is degrees of freedom 9. We're going to use DF9 here, and you can go to your calculator, and if you're trying to get an area under a curve, we would be using TCDF if your calculator has that. If not, you're stuck with the table. And although I don't have the table pulled up right in front of me, I can pull up the one from the last lesson here. Let's take a look at this. See if it'll allow us to zoom in. This is kind of tricky. So how do we use the table here? We want to use degrees of freedom 9 row, and we want to go and find the area underneath, you just do one side and then double it for a two-sided test. So I'm going to go to degrees, ignore the 8. We're going to degrees of freedom 9, that's from last lesson, and we're going to see where 1.604 falls between. 1.604 falls between 0.1 and 0.1 and 0.05 for the area here. And so if we know that it falls between 0.1 and 0.05, our p-value, that's just for one side. We have to double it, so it's really between 0.2 and 0.1 for our p-value, which is actually going to cause us to fail to reject. But how do we do that on our calculator? We would use TCDF. So I'm going to do that right now. So we're going to do TCDF, and we're going to go from 1.64 up to 1,000, and then we're going to take the area under that, and we're going to times it by 2, because that's how we find our p-value. So I'll just do that right now. So I'm going to do our p-value equals 2 times t CDF, back up. Oh, let me make this larger. Sorry, Class A. 2 times t CDF with lower equal to 1.604, comma, upper equal to 1,000, comma, degrees of freedom equal to 9, done. Okay. Now what this will give me is you end up, if you had just done to the right, if you just looked in the area to the right, you'll get a you will get an area under the curve, so it'll be 2 times 0.0716, which is equal to 0.1432. All right. We've got our p-value. So obviously our result here is based on the study, based on us assuming that that calcium and the placebo are going to have the same effect. We would expect to get the results that we got for a two-sided test roughly 14.32% of the time. And we'll do a official interpretation of that in just a second in context, because that's going to be fun. So what's our conclusion for the test? The conclusion is we reject H0. We reject that the means for the two populations, the mean and blood pressure reduction is the same. We're rejecting that. We failed to find convincing evidence. Hold on here. Make sure I'm doing this right. Whoops. To find convincing evidence to suggest that we fail to reject H0. Okay, we failed to, I don't know why I said that. We failed to reject H0. We failed to find convincing evidence to suggest that the mean in blood pressure reduction, systolic blood pressure reduction. If you make a mistake on the test, you can go back and fill words in, okay? In the mean and systolic blood pressure reduction for the calcium group for men like these who take, remember we're talking about the population here, we're not talking about our sample. For men like these who take calcium suggest that the mean and systolic blood pressure reduction for men like these who take calcium is, we failed to find convincing evidence that it is different than the mean for and systolic blood pressure reduction for men like these who take a placebo. Brutal. We failed to reject H naught, okay? We failed to reject H naught, I should say, as 0.1432 is greater than alpha equals 0.05. So that's our justification. Since our p-value is greater than alpha, we failed to reject H naught. We failed to find convincing evidence to suggest that men that the mean in systolic, the mean in systolic blood pressure reduction for men like these who take calcium is different than the mean in systolic blood pressure reduction for men like these who take the placebo. Brutal. I tried to make the context for this question particularly confusing just in case you have to try and structure one like that. I don't know if I want to end on that note. So how are we doing on time here? Let me take a look. Oh, we're doing good. We're doing good. Do you want to take a stab? We're going to take a stab at doing the p-value for this. This is, I think, what we're about to do is the hardest contextual thing that we've done in this class. I would like to try it and see how we do and kind of talk about this in terms of a randomized experiment. So what does this mean for our p-value? This means that if we were to essentially the p-value of 0.432 basically means assuming that H naught is true, right? Assuming, let's do it, remember p-value for Dylan was assuming he was an 80% shooter, what was the likelihood we got the results that we did based on us, based on our simulation. In this case, it's assuming, whoops, God dang it, the marker, need a hotkey for that. Try that again. So for this scenario, it's assuming, this is going to be a mouthful, the mean in blood pressure reduction for each pill is the same. Okay, assuming that the mean is the same. So assuming that H naught is true. This is H naught true. Assuming the mean is the same. Basically, before I write it, I want to do the basically. 14.32% of the time, if we had randomly put the people into other groups, then we could expect to get results like we did or more extreme than we did. 14.32% of the time. So how do we say that in the context of this question? Okay, so we're going to say we could expect to see a difference. Now I got to be very specific here. That is calcium minus placebo, since this was two-tailed, or placebo minus calcium. And the reason I have to do that is because it's two-tailed. You have to say both. Okay, we could expect to see a difference in mean blood pressure reduction of 5.273 or greater approximately 14.32% of the time. From random chance of reassignment. Treatment. Basically, if we were to repeat this experiment and we were to randomly shuffle the groups again, and we did that thousands and thousands and thousands of times, roughly 14.32% of the time, the random shuffling would cause us to get the results that we did based on our sample. Okay? That was probably the most complicated sentence we've written in this class. I don't want to end with this example, so we failed to reject. I'm glad I fixed that. We failed to reject H naught. Let's go ahead and see. Let's go back to that example we did on the previous lesson. Let's run a test on this really fast, and we're going to see what the p-value for this was. Remember, our confidence interval did not contain 0 for the boys and girls heights. Now, I'm not going to do state, plan, do, conclude here. We're just going to do the do and the conclude for this test in particular, because I want us to see a one-sided test. I will say that our hypotheses for this are that the heights are the same. The mean for the males minus the mean for the females is equal to 0. Our alternative hypothesis, we think that guys are taller than girls, so we would say that's what's reasonable to test, or that's what's being argued. Are men really taller than women in the question? So we would be checking to see if it's bigger than 0. That's our test. We know that the conditions failed for our data collection, so we can't actually do this test, but we're going to proceed anyways. T is equals the difference. Let me pull up the data from last time. Oh man, did I close it? I must have closed it. Hold on. There it is. All right, let's do this thing. Okay, so it is equal to, our test statistic is X bar for the males. Do we need to write this again? I'm not going to write this again. Let's just use the numbers. X bar for the males minus X bar for the females from our sample. So that is 70.67 minus 65.41 minus 0 over the square root of that really nasty thing, which was 2.578 squared divided by 12 plus 2.609 squared divided by 9. Okay, let's go ahead and do this on our calculators right now and make it happen. Home, that is 1.14. So I get in the numerator 5.26 for the difference here, minus 0. And then in the denominator, I got 1.14, we'll round up to 45. So we get a t critical value here of, let's do that, 5.26 divided by this number is 4.595. So 4.595 is kind of the number of deviations or standard errors we are going over on our t distribution. So let's draw that in a curve. All right, so basically, how rare are our results based on the distribution? So if this is our t distribution, ooh, that's ugly. We're going to go out 4.595. Whatever area this is right here, this is a one-sided test. We're testing over here. This is how, basically, how many standard errors our observed results are effectively this rare, and we need to look at the area under the curve to get our official p-value here. So let's do p-value. I don't like saying this rare about a t-critical value, so hold on. The p-value is, so if you want to use the table again, let's pull that t-table up. We're going to be using 8 degrees of freedom like we did yesterday. Let's zoom in. We got 4.595. So the area to the right for 4.595 is somewhere between 0.001 and 0.0005, both of which on our boundaries, since both of them are less than any alpha that we would use. We didn't really claim an alpha, which I kind of screwed up on, but if we say alpha equals 0.01, the range on our chart for for degrees of freedom 8, 4.595, that's between these two, so we know our p-value is somewhere between these two areas. Again, and if you were doing TCDF, you would do lower at 4.595, upper at 1,000 degrees of freedom is 8. So we get a p-value of somewhere between, okay, our p-value, so I'll say 0.001 is greater, which is, so the last one goes on the smaller side. So it would be 0.0005 is greater than our p-value. Our p-value is somewhere in there, which means we know that it's less, which means we can conclude that, which means we would reject H naught here. If we reject H naught, then that means we have convincing evidence to suggest that the mean height for males, senior males at NPHS, is actually greater than the mean height for females. And that should be kind of synonymous with the results we got from the confidence interval, because our confidence interval did not contain 0 as a plausible value for the difference between them. Okay, yeah, so let's go ahead and move forward here. If you want to do this on your calculator, then this is the method that you can do it. The easiest method, I think, to do it with is with lists. So you can plug in the lists of the data, and then you need to remember which one is in which lists, and then it will take the difference, and you can compare them there and check. Now just remember, the degrees of freedom that your calculator is going to use is not going to be the degrees of freedom that we used, because we're using the conservative estimate from the last lesson. The calculator uses a different formula, but it should give you roughly the same result, so you can still kind of check your answer there. And let's do an interpretation for this p-value really fast. When we actually do the test, let me plug in the test here. Let me get the actual p-value. TCDF, lower value is 4.595, upper value is 1,000 degrees of freedom 8. You get a p-value of 0.0008. 0.0008 is our p-value. So assuming that, if we assume that the heights from the populations are the same, based on our sample data, we would expect to see a difference as large or larger than we did between the boys and the girls, roughly 0.088% of the time. That's the interpretation for the p-value. If you want to write that down, take the time to write that down. If not, then we're good. We're all done. Thanks for tuning in, and you have your calculator instructions here. That was lots of fun, guys. Holy cow, we're almost done. We're almost done. We're gonna close the shop here soon. All right, guys, thanks for tuning in. I'm gonna go back to getting my work done. Back to the grindstone. All right.